at the University of Southern California, a PhD student. Thomas Linker at SLAC, Stanford, postdoc. E.A. Lowe, who you heard from before at Argonne, and professors Ken-ichi Nomura and Aiichiro Nakano at USC. We've been working together for some time on the optimization, enablement, profiling, performance, and results of the workload DC mesh, which is a very novel way of approaching light matter dynamics in the quantum dynamical space. So to that end, let me get started. So I will start today's talk with an introduction to light field dynamics first, so domain focused, followed by a discussion on various code transformations made on the software. Following this, I'll discuss a novel use case that we have that others might benefit from, which is the utilization of mixed precision in this traditional HPC workload. That is to say, we have FP32 for the majority of our GPU-specific portion of the application, and then bfloat16 for the matrix multiplication within the CGEMs, which account for the vast majority of the flop count and compute intensive of the compute, rather. And then after that, I'll go over some of the performance results that we have on Aurora, and then where we hope to go from here. Okay. To that end, DC mesh was actually developed over the last several years as a method to study light matter interaction, which implements an order of NDFT approach. This is done in two particular parts. So first one, by solving simple partial differential equations with differential operators acting locally, which we call local field dynamics, or LFD. This portion is the most compute intensive and is then localized on the GPU. The second part is where we carry out coarse-grained schemes to approximately describe complex chemical interactions, which we call quantum excitation molecular dynamics. And these can take advantage of complex instruction sets on the CPUs. To minimize data transfer between CPU and GPU, we adopt a shadow dynamics approach in which a GPU resident proxy is solved to describe the action of LFD on QXMD. In this way, the two halves have minimal exchange. And this combination yields a globally sparse and locally dense solver, wherein intradomain Hartree coupling is achieved via sparse multi-grid method and intradomain non-local exchange correlation. And that would be implemented via dense basic linear algebra subprograms, or BLES, which would be obviously the CGEMs. So continuing from this, the concept of utilizing the divide and conquer approach, which is the first two letters of the acronym DC mesh, needs a little bit of explanation. I feel that's important. So in DC DFT, the 3D space is a union of overlapping domains. We solve what's called the Kohn-Sham equation within each domain to obtain local KS wave equations. And in addition, the Hamiltonian then depends on the local electron density. So we sum all the domain densities with each being a sum of the local KS wave equations. Then continuing from this, as part of the setup of the basic algorithm, and within the general flow of the problem, the first intensive operation is to propagate the electron wave function. And the high-level view of this is that you can start with a known wave function for a given mesh S, and then you can pick a point from a set of points for an axis. So for example, if you pick a point I, then you can apply the stencil operation along the entire JK plane, and then you can update the wave function at the grid points and repeat this until you cover all the mesh points in the system. And how this applies then to an actual code block would be the following. So I'll take my time a little bit to go through this, but let's say if we break down one of the code blocks, we can gain some insight. So in this example, we perform reordering, blocking, and utilization of OpenMP to get a hierarchical parallelism in the kernel. So the first level of parallelism is achieved from the fact that the time evolution of a given point I requires just the knowledge of the wave function at the current time step and that of the previous time step. And that's within each plane. A second level of parallelism can be achieved from the propagation of the wave function independently for each orbital, and it's that particular component of the orbital size which will make the biggest difference in the actual performance when we run at scale, since that's one of the key factors that correspond to the size of the matrices within the gem calls or within the C gems, and that's where we can get the biggest boost in performance as we scale in Aurora. So if we dig a little bit deeper into that component relating to the C gems, where they come from can be seen in this slide, but the compute-intensive operation arises from solving the first equation that we see here. But what it means ultimately is that this is where the gem operation is actually calculated and where it originates. The gem operations itself correspond to the majority of the flop count, and then focus on minimizing their time to completion will allow us then to maximize performance. So I'm going to go through one particular operation that's very compute intensive, talk about how it is originally, and the following slide discuss some of the key optimizations that helped us to improve performance. So in this case, we're taking a look at one kernel, and in the divide and conquer approach, Maxwell's equations are represented on coarse spatial grid points centered up in domains. So the source term of Maxwell's equations is the electronic current density that you see here described. And the key computation is the spatial derivative of the wave functions. The data access pattern for the unoptimized code here, shown in this figure, where each thread does the finite difference sum by iterating over an ordered set of chaos orbitals for each spatial point. How we optimize this can be seen in the following code, in the following block. After one round of optimizations, we simultaneously iterate across distinct spatial grid points with matching chaos orbitals, such that an access pattern focuses on preserving data locality at a thread level while iterating across distinct spatial grid points. This is clear, this then allows us to observe the 15.5% increase in runtime efficiency when testing on up to 400 GPUs, in this case that you see in the inset figure to the right. Some of the other optimizations that we focused on, which helped a lot to reduce time to completion for this particular kernel, was the following. So the code previously used a single kernel for the entire stencil, but poor cache behavior that we observed was due to loop ordering. So additional complexity was due to the reuse of a single code path for all 3 dimensions. So for example, it's basically storing the strides in an array. In other words, the new code that we used to optimize was to apply the stencil in each dimension separately, using a rolling assignment of values to keep the previous, current, and next offsets in the registers for the current dimension. And we used empirically derived cache blocking factors to improve reuse. So with this, then, I go to the portion for mixed precision. So within the MKL library that we have as part of Intel 1 API, there's something called the MKL compute mode, which you can basically convert a float input matrix to one of a series of different precisions, in this case bfloat 16, x2, x3, TensorFloat 32, and then complex 3M. If we take advantage of this and apply it to the CGEM routines, the few that we have, which again are the bulk of the compute that we have in this code base, we can get a significant performance improvement. Of course, the slides that I will have ahead, we'll talk about what we lose in that process and whether that loss is acceptable. So with the shift in focus to alternative precisions, as we see it very common in AI workloads, an increasing need to apply this technique also to HPC workloads is something that is being worked on, and we hope to sort of push some insight to that effect here. So in float to bfloat 16, for example, MKL internally converts single precision input data to sums of 1, 2, and 3 BF16 values, depending on which one you chose, then uses the fast systolic arrays available on recent discrete GPUs to multiply the resultant BF16 component matrices and accumulate them in single precision, FP32. So as the number of bfloat 16 components increase, so does the expected accuracy. bfloat 16x3 will be generally almost as accurate as FP32. Of course, you lose a little bit. So what does this mean in the context of our workload? Well, here we're looking at a few different outputs directly from the code as we utilize these different compute modes for bfloat 16. And we're seeing how essentially that deviation from the reference FP32 is affected by each one. So in this case, we're taking the number of excited electrons, which is one of the major ones directly impacted by one of the CGEM blocks, compute current density, and kinetic energy. Kinetic energy generally is independent, but we can use this a little bit as a reference. However, it is to some degree also affected. Now, the kinetic energy plot may seem like it is actually quite significant, but bear in mind that the scale is important. So for kinetic energy, we're talking about orders of magnitude, 10 to the power 3, 4, 5. So a loss of just 4 atomic units is actually quite trivial for this particular number of atomic units in the time frame that we have simulated it. Similarly, the same can be said for current density and the number of electrons. Number of excited electrons typically that we're looking at is in the order of about 600, 700. So we're within 1. Again, for this time frame. If you run this for an extremely long duration, it's possible then you could get a significant buildup. Why aren't we seeing it here? Well, there's one reason really that's key, and that is that non-local corrections generally are less pronounced for the case where we're studying in this paper, namely these. And that's due to the fact that for every 500 quantum dynamical steps of LFG that we're running in FP32, we then execute the self-consistent field, SCF, which is at FP64. And that's used to update the wave function and then proceed to the next series of QD steps. So we are essentially preventing a buildup of truncation errors and preventing sort of the simulation from crashing. In that respect, that's one of the big reasons as to why this code is able to even run through the use of using these alternative precisions. Now, what does this do for performance? Regarding performance, we basically split it up into 2 parts, depending on the size of the problem. I want to focus first on the right graph here. Now, as I mentioned before, increasing the number of orbitals of our problem is a big factor in improving and basically increasing the size of the gems and therefore increasing the compute intensive nature of the code and where this can benefit the most from. So for the largest sizes of an orb that we're able to fit within the memory of a single tile of PVC, that's about 4096. And for the case of using float to BF16 conversion, we can see up to about 4x, which my colleagues in the MKL team told me is pretty much approximately what they see. In theory, it should be 16x improvement over FP32. You won't see that, of course, because of power constraints and other factors as well. On the figure to the left is its impact in time to solution. And what we can observe, even at scale, even after running this system on Aurora with 10,000 nodes, 60,000 PVCs, we are able to get about I would say somewhere between 20 and 40% improvement in time to solution, a very significant improvement, and it works. The outputs are still within the degree that we would consider reasonable and not out of bounds necessarily. So, as it pertains to scaling, in this particular slide, we have recently submitted our Gordon-Bell proposal for this project. This data does not reflect the most up-to-date version because it is under review, but we look forward to sharing those later in the year. But what we have had earlier this year was scaling up to 50,000 GPUs, very high scaling efficiency of around 99%, I think. And then you see on the left strong scaling, on the right weak scaling. On the bottom, what we have had for flop per second performance. This would be on a single tile, and it includes the use of FP32 with bfloat 16 for the blast calls. With up to 55.26 in this case percent of FP32 peak flop performance on a single tile of Aurora, which has 448 EUs. We have a very good performance with this, and there is, as you can see, a significant improvement over the base case of FP32. The data that we have submitted for a final review for Gordon-Bell is quite a bit improved over this, since we have introduced new CGEM routines into the code since that time. In conclusion, then, we went over the basics of light field dynamics, the basics of what our code base DC mesh is all about, how we went about improving performance of the gems specifically, some of the optimizations that we did, and how we introduced alternative precisions into those CGEM routines, and where we are earlier this year with regards to performance in Aurora, and we look forward to sharing more later in the year. Thanks.
Good. It was really interesting. So it's good to hear real world stuff on Aurora at this point too. So it's been a long road. So let's see. I don't think we have any on the chat. If any panelists want to ask questions. So I one of this kind of, how generalizable is this, do you think, to other applications?
It very much depends on your code. I will not say that this is some sort of miracle that you can use in any code that uses CGEMs and that it will work. Not necessarily, not at all. For this particular case, it works simply because we reset the wave function every few hundred QD steps, and we can get away with it. I don't know, for example, how this would run if you were to do it on QMCPAC. It's possible it wouldn't work. So I would not say at all that it's generalizable, but it does work for us in this case. It seems to work quite well.
And how important do you think the memory architecture of the Aurora nodes are to this?
Basically, of course, the performance that we would get would only improve if we're able to fit more into the memory that we have.
Right.
But simply because the CGEMs continue to just improve up to a point, as you saw in this case, up to about 2,000, 3,000 in orb. That's the maximum that we can fit. Of course, if we could add perhaps a little bit more, that would be good. But thus far, it's been sufficient for our needs. We maxed out as far as we could, which was about 4x improvement over FP32. I don't think it would be possible really to get any more. Adding more would marginally improve performance. You wouldn't really get much benefit out of that.
Okay.